Welcome to video number 3. Yay! So this last one is the whole point of this entire series, is that we're trying to figure out how to balance these redox equations. So we've done all kinds of different equations, and this is the last equation type that we're covering for chapter 4. So with that, we be able to look at an equation, know that it needs balancing, but then we also need to consider not only did mass balance, but did charge balance. So this is a whole systematic step of how do we go from an unbalanced redox equation to a balanced equation. And these are the most simple types that we can possibly do. So in Gen Chem 2, we'll throw in extra oxygens and extra acids, and it'll get a little harder, but right now we're keeping it simple. Let's just say, where did those electrons go? And let's figure out where they went. Okay? So on the top of your worksheet is a whole bunch of steps. Read through those, pause the video if you will, and I'm going to go through each of these and talk about what we're doing and when. So the first reaction is iron reacting with copper, and we need to figure out how to balance it. So this is our first equation we're going to work with. Before we start doing the redox, I'm just going to remind you of oxidation numbers. So meaning, iron goes from 0 to +2, while at the same time copper goes from 2 plus to 0, which means this one, iron, was oxidized and copper was reduced. You should already know how to do this from the previous videos. So if we start back from scratch, we've got this balanced equation. I want to follow the steps just as I laid out. Okay, so first off, I already know that my copper is going to be reduced and my iron is going to be oxidized. But I want to write what's called half reactions. So what I do is I break them in half, meaning I put my iron species all by itself going to whatever ended up over here. If it would have gone to like iron oxide or something, you would just note whatever its oxidation state is within that molecule. But we're not going to make it that complicated. We're going to stick with simple stuff. So iron is going to iron 2 plus, copper 2 plus is going to copper. So in this situation, I always leave a little bit of room so I can put electrons wherever I want. Now we can add electrons to either side of the reaction. I never put a negative electron. I'm going to add them because I'm going to give them to a species, or I'm going to take them away, and if I'm taking away, I'm producing electrons. So electrons are either a product or a reactant, and they should balance, meaning if electrons are a reactant here, they should be a product here, or vice versa. Okay? So in this case, we look at the charge. It's 0 and 2 plus. Electrons are negative, so you always want to put them on the side that needs to be reduced. Meaning, if I put 2 electrons over here, I've added 2 negatives here, and it's still 2 plus over here. That is not balanced at all. So if instead I add my 2 electrons over here, now I've balanced this half reaction. Total charge on the left is 0, and total charge on the right is also 0, because you have 2 plus 2 negatives gives you 0. Same way over here. If I add 2 electrons to this side, this whole side equals 0, as does this side. So also notice that my electrons are on the opposite sides of the reaction. Now remember, we already talked about the fact that this goes from 0 to 2 plus, so this is my oxidation, and this is my reduction. If you look, anytime you have electrons and they are a product, that's always oxidation. If your electrons are written as a reactant, it's always reduction. Because you're adding electrons, reduction is gain of electrons, or a decrease in oxidation's number. 2 is going to 0, decrease. So all of these definitions work together really well. Okay? So now, that was kind of steps 1 through whatever. Okay? But when we're writing our half reactions, we also need to make sure we always start with balancing our atoms. So iron, iron. There's 2 irons, 1 on each side, so my atoms are balanced. And then I went through and balanced out my charge. Okay? And then the next step is that I need to balance my 2 half reactions by multiplying each equation by the lowest common multiple. Meaning, I need my number of electrons in each equation to be the exact same. If they're not, you can multiply entire equations by numbers to make it so that my total balanced electrons, this one's giving up the same number as this is receiving. okay, or backwards. This one is receiving the same number that this is giving up, okay? So electrons are literally flowing from iron as it becomes Fe2 plus to copper to become copper 0. That's literally what's happening. So, long story short, this is my oxidation half reaction. This is my reduction half reaction. They need to balance, meaning electrons are now on both sides of the arrow so they cancel out. And now I just add my two equations together, re-put in what the states were originally, and I'm done. So this would be Fe solid plus copper 2 plus aqueous yields Fe2 plus aqueous plus copper as a solid. Okay? It's actually the exact same equation as what we started with, but we had to go through this to prove that was in fact balanced. They're not all this simple. Okay? Alright, so now let's look at this example here. This example has tin reacting with silver to produce tin and silver. So we have one atom of tin, one atom of tin, one atom of silver, and one atom of silver. So it appears balanced from a mass standpoint, but if we look at the charges, we know it's not balanced because we have a total of +2 over here, and we have a total of +1 charge on that side. So it's not balanced. So we need to balance it. So first we write our individual, we separate our species and write our two half reactions. So we have SN2 plus going to SN, Ag going to Ag plus, and now I need to figure out where do my electrons need to go. So if I add electrons here, plus 2 electrons, and I chose 2 because of the charge, 2 plus 2 minus gives me a total charge of 0, and the charge over here is 0, so I'm balanced. Here, I know that I'm probably going to need to add my electrons to the other side because once again, they're added to one side and then the other. It's a pair. So over here, I'm going to only add 1 electron. Because of the fact that it's +1, I needed 1. So now I look at this and I first said, okay, I already balanced my atoms. My electrons, they're not balanced because I have a 2 and a 1. So I can't just put a line through both of them and move on. I have to balance them. And how I balance them is my lowest common multiple. Meaning, if I multiply this whole equation by 1 and multiply this equation by 2, now I can have the same number of electrons being transferred across the two half reactions. So this will stay the same. Here I need to multiply everything by 2. That 2 has to go to every species, including the electrons. Okay? So now my electrons cancel, and now I add them together, and I have a balanced chemical equation. So when I'm all finished, this is what it should look like. Tin2 plus aqueous plus 2 silvers solid yields 10 solid plus 2 silvers as a solid. Alright, here's the next equation we're going to do. Once again, note it's not balanced as far as charge goes. It's not even balanced as far as atoms goes. Okay, that's a really good thing to note right here. I have 2 iodines and 1 iodine over here. Not balanced. +4 on this side, +2 on this side. Not balanced. So let's write the half reactions. So here are my half reactions. I first suggest you start by balancing the atoms. It'll save you so much error. Okay? So in order to balance them, we can put a 2 in front of this iodine, and now I have 2 iodines, I'm good. So now I need to figure out what side do I put my electrons on. I put them on the side with a greater positive charge. Okay? So now I have a total of +2 over here, +2 over here. My iron is balanced. Over here, 2 negative, 0. So +2 electrons. I hope at this moment now you're thinking my electrons are not balanced. So I need to multiply one of them by 2. Okay, so this becomes 2 plus 2 plus 2. And now I can cancel out my electrons and add the whole equation together. So in the end, you should have 2 Fe3 plus aqueous plus 2 I minus aqueous yields 2 Fe2 plus aqueous plus I2 as a gas. So this is kind of the whole process. Sometimes you might want to do a 2 and a 3 or a 5 or a 1, I don't know. But you just multiply it by whatever numbers you do, you need to make these electrons cancel out. Okay? So now I want you to try number 18 and number 19 on your own, and then you will be turning it in on class on Monday. Have a great weekend.